Today I am going to talk about chapter 10 and 11 of my own book. So far, let me remember what we want to do. So we want to capture the Hodge theory of hypersurfaces by looking at its affine part. For this reason, we landed on the notion of a Tame polynomial. In my book, this notion is a little bit more general, but for our purpose, we just need this. So it is a polynomial in x1, x2, xn plus 1. And when we write it, it's decomposition into homogeneous pieces. We need this last homogeneous piece Fd. I will rename it as G. So F is tame if let's say, with the version algebraic, C x Jacobian of G is a finite dimensional C vector space. And at the end of the day, this notion is just this transversality notion that we had. So let me recall it. When we have a look for f equal to 0 in inside Cn plus 1, and we compactify the Cn plus 1 inside Pn plus 1, and then there is this Pn at the infinity. The tameness is just that my f intersect the infinity transversely. So this is there is this f equal to intersect the projective space at infinity transverse. So this is just the algebraic way of saying this geometric notion. Okay, so we are going to do a little bit some purely algebraic stuff. In particular, here I will in my book I have put, instead of complex number, ring R. So for example, ring R. And at the end of the day, we just need this, well, in my book I have put Cohen-Macaulay, so there are a lot of algebraic concept going on, but for our purpose we can put R equal to C, rational numbers, and another ring which is important. We will need families of hypersurfaces, so I will put this RC polynomial ring with some parameters, some variables, tk, and probably we have to invert some elements in this let's say let's say polynomial T1 tk polynomial. And this, in the same way, the tameness, instead of vector space, we have to say that this R module must be finitely generated. And then something also that really we don't need the complex coefficients here. What everything that I will tell today even works with if you work with the if you put here rational coefficients. Okay, so this is let's say this Vg, this quotient, Jacobian ideal G. is sometimes called the Milnor vector space, but once we are using ring here, so let's call it Milnor modules. So they are R modules actually. And okay, so okay, so from this point on, the course is going to be more computational. So this means that at the end, if something is finite dimensional, we have to choose bases because we want to implement in the computer and so on. So let me fix this notation, x to the I is a monomial basis of Vg. So I will also use this this just a different notation. So I will choose monomials beta is this index set, and at the end x beta, remember that it is x beta 1, x1 beta 1, x2 beta 2, xn plus 1, beta n plus 1. And Rx at the R module is generated by monomials, and we quotient it by this Jacobian, and we can choose this spaces of monomials for this G, for this Vg. So if I think maybe for simplicity, if you want just to follow the lecture with the, let's say, complex number. So it's okay. What else I need? Okay. So the topology of f equal to 0. Remember that we already done in the first 5 lectures of the course. Just this is before going to too much purely algebra stuff. Remember that f equal to 0. In the case f equal to 0, smooth, and f in Cx. Remember that Hn plus 1, Cn plus 1, and with boundaries in let's say f equal to 0. This with coefficient in Z is freely generated by, and actually let me introduce another norm. Mu will be the dimension of or rank of Vg. Rank of Vg freely generated by mu Lefschetz symbols. And remember that there was this we made this, and then anyway the first part of the course we invested a lot to try to prove this statement. So at the end of the day, this implies that Hn f equal to 0 is freely generated by mu Lefschetz vanishing cycles, and remember that Lefschetz vanishing cycles, they are just spheres. And so the topological part we have already seen. So now we are going to see the algebraic part, which is will be the de Rham cohomology of f equals 0. So today we will focus on this. Okay, so okay, maybe our main example. Maybe maybe I put also the main example. The main example would be, for me, the G will be this Fermat variety. Xn plus 1 to the D. And at the end, F will be G plus a lower degree monomials. And in particular, if I want to specify something here, F will be x1 plus d plus x2 plus d plus xn plus 1 plus d. But this is plus homogeneous, but then plus 1. And when we projectivize this f equal to 0, we will get the classical Fermat variety. Instead of 1, we will have x0 to the d. So this is our main example. And at the end of the day, let me x to the I basis in this case. This, let's say, Jacobian of G is what? Is just dx1, d minus 1, blah, 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 d xn plus 1, d minus 1. So this means that all powers of xi's bigger than or equal to d minus 1 will be 0, and at the end, so if we make this, let's say, if we form this Vj is freely generated by what? x1 to the beta 1, x2 to beta 2. Let's write it explicitly. Beta n plus 1. And then beta I is less than d than or equal to d minus 2 and bigger than or equal to 0, because all the powers of d minus 1 are 0. So if you want, you can also follow the course just with this example. Okay, so before going to describe the de Rham cohomology in this case, well, for the proofs we will need a lot of smaller statement. Maybe, well, I'm not really planning to prove whatever proof exists in my book. Actually, I'm planning to talk more about the computer implementation of this statement. Anyway, let's review the statement that we needed. What is statement de Rham Lemma? Maybe. Okay, I will use. Okay, maybe I will use this strange shift theoretic notations, but at the end we don't need really to go to just keeping in, I want to keep the notation used in my book. So, well, it doesn't matter what is A, what is T, but at the end it is differential forms. Differential, this is differential forms, K-forms in x1, x2, xn plus 1, and let's say algebra polynomial. So maybe let's write explicitly, these are just some pi x dxi1 blah 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 dxik, and then pi x, this is just a polynomial in x with coefficients in my ring R. So this is just algebraic geometric notation. There is some variety. T is the spec of R, but let's do not bother ourselves with this too much algebra. And okay, then this okay. So if you want to cut this A over T, doesn't matter, that you can do it. Okay, so the Rham lemma for G. So maybe this we will need it. Let me write it. Omega k plus 1. Let's put A over T. Here is dg wedge. This means that omega maps to dg wedge omega. So we have this complex, and the Rham lemma will say that at the end the sequence is exact. So if dj wedge omega is 0, then omega must be dj something, dj wedge something. Well, it is called the Rham lemma because at first it is done in the infinity context, but you see that this lemma can be stated even for arbitrary ring, so we don't need really topological picture here. And well, its proof maybe one good source is Eisenbach's commutative algebra book, but I have put also more references. So for the moment, I don't want to bother myself with too much algebraic proofs. In particular, I had promised to do Griffiths' theorem, but I skipped also this one. Okay, maybe let's keep in mind this one. So this will be at the end. If dg wedge omega equal to 0, then omega must be dg with wedge something, some other differential form. Okay. Maybe another statement which it is good to know. This another, let's say, the round proposition. Maybe this is proposition 10.3 in my book, and then proposition 10.6. Okay, the same proposition, the Rham lemma for f for Tame polynomial. Theorem is valid for Tame polynomial. So the point is that you see that G is here a homogeneous polynomial. But the idea is that if we perturb it with the lower order monomials, and then we will have the notion of this Tame polynomial, then still if df with omega equal to 0, then omega must be df with something. And I mean, the proof, once you assume the Rham lemma for G, this is a straightforward, purely algebraic proof. You have just have to say make the control of lower order monomials. Okay, so maybe for the moment it is just good to know this statement. Maybe one non-trivial statement, and at the end it will be useful for our purpose. Remember that I choose a monomial basis for Vg, and maybe I write this proposition for this is proposition 10.7 for a Tame polynomial, the R module Vf is generated freely by xi. Remember that this x to the I were the basis of the Vg, and now the claim is that the same monomials also they give a basis of a Vf, and so we don't need so the choose of a basis of Vf just depend on the last homogeneous piece of f. If we fix a basis for Vg, it will be done also for Vf. But of course, in our main example, it's trivial because the Jacobian of this f, since there is a constant here, is the same as the Jacobian of G, this part. So this proposition in this case, it is trivial. But I think it would, since we will be interested on deformation of the Fermat variety, it would be nice to carry in mind this one. Once really we start to using it, it would be nice to have a look at its proof. So for now, I will not also focus on the proof of this one. It is it's almost a page and a half in my book. And by the way, I have to say that all these ideas of Tame polynomials come from singularity theory. And maybe if not by looking at this ring, just complex numbers, but and I have just made this adaptation to the global context, but because we at the end we are interested on the Hodge conjecture for hypersurface. Any questions so far? Okay. So another concept that it is also nice to have in mind, that the discriminant of f. F will be always for me the Tame polynomial. Okay. And actually, this way I presented the discriminant. I don't know if I have not seen in this way in the literature, but well, okay, let's do it. So we have this VF, and I am going to define a map from VF to VF. What is this this map? This is, if I just have polynomial p, I will just multiply p with f. It is just multiplication by f. So this is a well, this is a finitely generated. This is a free R module, and I'm particular write A in the basis next to the I of VF. So A will be a matrix at the end. This means that A, what will be? It will be a matrix mu times mu. Mu was the rank of VF. And which coefficients? It will be R module, so this will be coefficients in R. So once again, if for this ring, if you want, you put just complex numbers. And so you have this matrix, and so once you have a matrix, you define this as sorry for twice using S. One is the capital S, the other one is smaller s. Determinant of I minus S identity matrix mu times mu identity matrix. So this will be a polynomial in S, polynomial of degree S degree mu. Actually, the mu comes from the Miller number, mu of degree mu in S. And okay, so well, I will need this SS, but at the end for the definition of the discriminant delta, let's say delta F, it will be just the determinant of A, which is just S0, and it will be in this ring R. Okay, and well, what is the role of this? Well, this discriminant. Maybe this one actually I will. It is easy to prove. Proposition is a 10(8). So well, let's go to the let's say R. Let's go to the complex number, uppercase. Then delta F. So in this case, delta F equal to 0 if and only F equal to 0 is singular. So in some sense, delta F not equal to 0 parameterizes is smooth F equal to 0. And so the proof is actually easy. Okay, so let me. So for example, let me say let's do the first this one. Okay. For example, if let's try to prove this one. If it is singular, then delta f must be not equal to 0. So if delta f not equal to 0, what this means? This means that A is surjective, because determinant of A is not equal to 0. In particular, this means that the number 1, is in the image of A. So what this means, that 1 is equal, so it will be some 1 is equal to f some polynomial p, but of course modulo the Jacobian. This means that this we will have some identity like this. So there will be some polynomials p and pi, such that this is valid. P, pi, all polynomials in Rx, and this will imply that at the end this and this polynomial they cannot have common 0, and then f is smooth. Okay. And the other direction is also easy. You just have to understand the characteristic of them. So delta f equal to 0. It means that f equal to 0 is we have to show that f equal to 0 is as a singular. If let's say G game is smooth, so then this what is this means that this variety f equal to 0 and all these partial derivative equal to 0, I equal to 1 until n plus 1, this is empty. And so by Hilbert Null-Stellensatz what we have then, the one belongs to this ideal. So there is 1 equal to f some 1 belongs to this ideal, and when we write it in VF, it will mean that 1 equal to 1 fp. This f in VF for some polynomial p, and then we conclude we conclude that is not equal to 0, because it means that I is invertible. Anyway, this we will need the notion of the discriminant introduced in this way. So you see that even we can compute it. Next lecture, one of the things that I will do it. I will show the computer implementation of all the spaces x to the I, discriminant, and so on, to show you that everything now that we are talking about can be implemented in a computer, because at the end we want to do a little bit of computational Hodge theory. Okay, any question? Okay. So for examples of discriminant and so on, in the next year I will show it in the computer. Okay, so the main purpose of our lecture today is to go to the de Rham cohomology. So the formulation of the de Rham cohomology in this context, it is called Brieskorn modules. So Brieskorn module is just a kind of de Rham cohomology of affine varieties, but it's a kind of finer version of de Rham cohomology. Brieskorn. And these concepts, once again, it is mainly used in local context in singularity theory, and I have just made the adaptation to global context of Tame polynomials. Okay, so again, F Tame. Maybe I start from this Brieskorn module. So just remember that at the end we are interested on H and de Rham. And by Atiyah-Hodge theorem, let's by Atiyah-Hodge theorem, what is this? This is just differential n forms. Differential n form in the ambient space. At the end, if you want to replace this notation with just, let's say, Cn plus 1, that would be okay. But I want to emphasize that at the end, we can do our ring, arbitrary ring. So this is n forms, but of modulo what? Modulo exact, modulo differential form which restricted to f equal to 0, they are identically 0. In particular, I have to cut out these guys because this restricted to f equals 0 is 0. And also df, because df wedge omega n minus 1 also restrict to f equals to 0 is equal to 0. And there is another term coming because of the de Rham cohomology, modulo exact forms. Differential of these guys. So by Atiyah-Hodge theorem, when I am my ring is just a ring, the field of complex numbers, then this de Rham cohomology is controlled by this quotient. This is because of just the restriction, and this because of the definition of the de Rham cohomology. But now I'm doing a little bit in a more general context of polynomials. So if f is a tame polynomial over the ring R, so I will denote this one by h prime. This is h prime is an R module. So when R is the field of a complex number, then this is really just the de Rham cohomology. And by Atiyah-Hodge theorem, it is finitely generated and so on, and there is no problem. And but it turns out that in this finer context where we use rings, we can introduce other modules which becomes also useful, and at the end they are the same as de Rham cohomology. In a minute I will explain. Maybe I write this one. So for the moment, forget this this notation, because I want to consider them as R modules. And for the algebraic de Rham cohomology, I was supposed to work just with the fields of characteristic 0. If I wanted to use rings, I had to go to the languages of sheaves and so on, sections of cohomology bundles, blah, blah, blah. But for the moment, just forget this one, and let's, instead of the Rham cohomology, just keep to this Brieskorn module. Maybe I write also the other module, Brieskorn module, and I say that this is also essentially the Rham cohomology. So n+1 forms. I will cut writing this a over t. And what else? F. So those which are multiple of these guys plus the f which the and it turns out that this is also a nice module. So you see that n+1 forms modulo those which are multiple of f, and modulo those which are df wedge of d something. And in a minute, I will say why this is useful. This corresponds to our our algebraic presentation of the Rham cohomology, but this not, because at the end, with this one also we want to capture n the Rham cohomology, not n+1. By the way, you see that we are focused on n because above n and below n there are no interesting the Rham cohomology. All of them are 0. I have not talked about this one, but we will focus on this n, and the n is the dimension of equal to 0. Okay, so okay, so this is also this R module also is basically the Rham cohomology. Maybe I introduce a map. H prime. This map in our complex context will be isomorphism, but in our algebraic in general context will not. So this omega going to df wedge omega. This is the well-defined map. So maybe let's to check the well-definedness. If you make df, then it is multiple of f. It is 0 here. It is 0 here. If you make a df of this guy, this will be 0, so that will go to 0. And if you make df of this guy, you will land here. So at the end, this is very defined. And okay. So maybe proposition 10. If delta of f is, if the discriminant is not equal to 0, for example, if f is equal to smooth, then the map is an injection and actually so this means that the end this will be inclusion, and okay, so H. So under this inclusion, I will consider H prime as a submodule of this guy. By the way, all these things are at the end are modules. This will be isomorphic. Let me combine. this will be isomorphic to, let me write it explicitly. Remember that for the Milnor vector space, we divided by Jacobian of F, but this quotient will be Jacobian of F, the ideal generated by Jacobian of F and F itself. In some sense, if I want to write it in terms of, so this will be VF F times quotiented by F times VF. And well, let's just a moment. I have oh, I have made a mess with a minute. Yeah, okay, yeah. Okay. Again, well, the proof is purely algebraic even for arbitrary arc when McColoring, etc. What is the moral of the story for our purpose, for our geometric purpose? So remember that when delta f equals, so let me say in this way. For example, when R is the field of complex numbers, remember that this multiplication by f was surjective. At the end, this will be R equal to C. So in the case of R equal to C, it is H prime is isomorphic to H double prime, just on this omega going to df wedge omega. So at the end, H prime is the same as omega by this, and this is not again, it's not really hard to see. So, but anyway, well, the moral of the story is that this is also over the Rham cohomology. But what we have to do in order to get differential n form, each time we have to divide our n+1 form over df. And the reason for this is, okay, maybe let's say actually the other case also. Maybe I have. If we want to be purely in the algebraic framework, and delta f not equal to 0, but by definition of this preeminent, delta f multiplied by this vf quotiented by f vf is 0. So discriminant is the 0 divisor for all elements here. And for this one, really, you have to go to the definition of the discriminant. You see, delta f is just the determinant of a multiplication by f, and if you multiply it, let me say in this way, if you multiply any element in VF, it will be in the image of your map. This is you just get it from the definition of discriminant. So what I want to say, maybe in a general context, H prime is embedded inside H double prime, omega going to omega wedge df. And once you want to return back, for example, if you have element in H prime, let me say in this way, if you have elements in H double prime, delta f and omega always will be of the form, this will be in H prime, it will be df wedge omega prime. Okay, and the reason why we use this H prime is that, let's say, at the end of the day, we want to integrate, you want to capture Hodge theory by these integrals. Just maybe I remember this Hn, let's say, let's call L f equal to 0, or f equal to 0, and omega in Hn the Rham L. And so for let's translate to Gil and Leray form. So, okay. When we have this omega in H prime, we can introduce this omega divided by df, which will be omega prime divided by discriminant. This will be in the localization of the Brieskorn module H prime, our delta, because we are making the quotient. This will be the localization, our 1 delta, delta 2, this multiplicative set. And where omega delta is just df omega prime. And at the end, we can now talk about these integrals. And so, whenever we are talking about this integral, we mean actually the language coming from the Brieskorn module. And actually, this is a better way to talk about many examples of integrals before Hodge, in Picard's book. Maybe I mentioned this one. Let's write omega, for example, omega. Let's write omega as I have put G, but that's not it. That's a P dx1, dx2, dxn plus 1, P, a polynomial in X, if you want to put it. And okay, so here I made a process to divide our df, but around the Picard time, the process of dividing our df was something like this: omega df. This is really a division, so it is a p dx dxn. So xn plus 1, let's just multiply the denominator and numerator by partial derivative of fxn plus 1. Okay, so df. So here we can put it df here. So once you say that, okay, I am allowed to divide on polynomials also, because so far I was avoiding to make this kind of division, then you can do this one, and then basically you will get this one, and at the end the p, it is p dx1 dxn divided by fxn plus 1. And this is the, let's say, this is the old way of writing writing many multiple integrals. dx1, dxn divided by partial derivative of f, and the people around the Picard, the time of Picard, they were trying to understand these integrals, which are also called periods. Okay, so okay, so maybe let's mention the main theorem. Okay, but Atiyah-Hodge theorem, when we are when the R is the field of complex numbers, I know that all these things are finitely generated, vector spaces, and so on. But it turns out that in this even in this general context of arbitrary ring, we can make some nice statements. And then let's I write the main theorem, and okay, so this is a theorem 10.1 in my book. Let me see. Okay, and so what is the point? I will write a very short version of the theorem. So H prime is free R module. So by the definition, they are not, it's not at all clear whether they are free or finitely generated, but it turns out that is the case. Free R module generated by eta beta. So remember that we took a basis I. Remember that we took this x beta in I, a basis of the Milnor module of G. So it will turn out that this, from that one also we can construct this the basis for H prime. So this eta b is just x to the beta monomial coming from there, and then then differential form I equal to 1 n plus 1 minus 1 to the I xi dxi check. And remember that dxi check was the product, wedge product of all dxi except dxi. And in a similar way, H is free R module generated by omega beta. Omega beta is just OX beta dx1 dx2 dxn plus 1. And okay, so maybe I go to, so let's go to the page of my book. I think maybe present now your window. So the proof of this, so as you see in my my book, that I've tried to write down everything for arbitrary Cohen map coloring, and for this reason that it has become a little bit longer, but and so this this notation eta beta omega beta iron 2, we will call this eta. Maybe I remember this notation. This let's say this eta dxi check Mu was the rank. We will need also this this number A beta. In our context, these VI's are all 1. And so let's go further. So today just a little bit talked about this stuff. Let's go to the proof. Let me see, discriminant. We already told about discriminant. Examples of discriminant is computed. Next lecture, I will try to do a presentation of my codes for these things. So you see that the main theorem, actually, I have put more details. Okay. So they are bases, but at the end, when I want to write omega in terms of omega betas, they are in the Brieskorn module H prime. So there is some these F's also. It's modulo these guys. And then there is some statement about how these must look like. But just don't worry about this. And the proof is purely computational, in the sense that even I have implemented the proof in the computer. So we can, whenever I have an element in the Rham cohomology, it's possible to compute the basis. Next lecture, I will explain this one. So I will not try to even write down the proof, because even myself, I have forgotten the proof. But the good point is that I have implemented the proof in the computer. And that is one of the reasons that I let my mind forget the proof, because now the computer computes for me. Okay, so this is the very concrete situation for the Atiyah-Hodge theorem, in which we have a basis of the Rham cohomology, and we can even write everything in terms of this basis in practice and not in theory. Okay.